bytes means you'll be in a much stronger position when you're faced with interpreting untyped bytes flying in from the network throughout your career. Section 5.5. Fixed point number formats. In addition to representing decimal numbers with floating point formats, fixed point is also available. These can be useful for representing fractions and are an option for performing calculations on CPUs without a floating point unit or FPU, such as microcontrollers. Unlike floating point numbers, the decimal place does not move to dynamically accommodate different ranges. In our case, we'll be using a fixed point number format to compactly represent values between -1 ... equals 1. Although it loses accuracy, it saves significant space. Footnote 2. This practice is known as quantizing the model in the machine learning community. The Q format is a fixed point number format that uses a single byte. It was created by Texas Instruments for embedded computing devices. The specific version of the Q format that we will implement is called Q7. This indicates there are 7 bits available for the represented number plus 1 sign bit. We'll disguise the decimal nature of the type by hiding the 7 bits within an I8. That means that the Rust compiler will be able to assist us in keeping track of the value's sign. We will also be able to derive traits such as partial EQ and EQ, which provides comparison operators for our type for free. Footnote 3. Q, often written as Q, this style is called blackboard bold, is the mathematical symbol for the so-called rational numbers. Rational numbers are numbers that can be represented as a fraction of 2 integers, such as 1/3. The following listing, an extract from listing 5.14, provides the type's definition. You'll find the source in this file. A struct created from unnamed fields, for example, Q7 of I8, is known as a tuple struct. It offers a concise notation when the fields are not intended to be accessed directly. While not shown in listing 5.11, tuple structs can include multiple fields by adding further types separated by commas. As a reminder, the #derived triple dots and square brackets block asks Rust to implement several traits on our behalf. Debug, used by the println macro and others, allows Q7 to be converted to a string by the : syntax. Clone enables Q7 to be duplicated with a .clone method. This can be derived because I8 implements the clone trait. Copy enables cheap and implicit duplications where ownership errors might otherwise occur. Formally, this changes Q7 from a type that uses move semantics to one that uses copy semantics. Partial EQ enables Q7 values to be compared with the equality operator, or equals. EQ indicates to Rust that all possible Q7 values can be compared against any other possible Q7 value. Q7 is intended as a compact storage and data transfer type only. Its most important role is to convert to and from floating point types. The following listing, an extract from listing 5.14, shows the conversion to F64. The source for this listing is in this file. The two IMPL from of T for U blocks in listing 5.12 explain to Rust how to convert from type T to type U. In the listing, lines 4 through 18 introduce the IMPL from of T for U blocks. The std convert from trait is included in local scope as from, which is part of the standard prelude. It requires type U to implement from that takes a capital T value as its sole argument. Lines 6 through 7 present an option for handling unexpected input data, crashes. It is not used here, but is available to you in your own projects. Lines 13 through 16 truncate out-of-bounds input. For our purposes, we know that out-of-bounds input will not occur, and so accept the risk of losing information. Tip: conversions using the from trait should be mathematically equivalent. For typed conversions that can fail, consider implementing the std convert try from trait instead. We can also quickly implement converting from F32 to Q7 using the from of F64 implementation that we've just seen. The following listing, an extract from listing 5.14, shows this conversion. Its source is in this file. Now, we've covered both floating point types. But how do we know that the code that we've written actually does what we intend? And how do we test what we've written? As it happens, Rust has excellent support for unit testing via cargo. The Q7 code that you've seen is available as a complete listing. But first, to test the code, enter the root directory of the crate and run cargo test. The following shows the output from listing 5.14, the complete listing. The following listing implements the Q7 format and its conversion to and from F32 and F64 types. You'll find the source for this listing in this file. A brief look at Rust's module system. Rust includes a powerful and ergonomic module system. To keep the example simple, however, this book does not make heavy use of its system. But here are some basic guidelines. Modules are combined into crates. Modules can be defined by a project's directory structure. Subdirectories under src/ become a module when that directory contains a mod.rs file. Modules can also be defined within a file with the mod keyword. Modules can be nested arbitrarily. All members of a module, including its submodules, are private by default. Private items can be accessed within the module and any of the module's descendants. Prefix things that you want to make public with the pub keyword. The pub keyword has some specialized cases. A. Pub crate exposes an item to other modules within the crate. B. Pub super exposes an item to the parent module. C. Pub in path exposes an item to a module within path. D. Pub self explicitly keeps the item private. Bring items from other modules into local scope with the use keyword. Section 5.6. Generating random probabilities from random bytes. Here is an interesting exercise to test the knowledge that you have developed over the preceding pages. Imagine that you have a source of random bytes, U8, and you want to convert one of those into a floating point, F32, value between 0 and 1. Naively interpreting the incoming bytes as F32 or F64 via mem transmute results in massive variations in scale. The following listing demonstrates the division operation that generates an F32 value that lies between 0 and 1 from an arbitrary input byte. As division is a slow operation, perhaps there is something faster than simply dividing by the largest value that a byte can represent. Perhaps it's possible to assume a constant exponent value, then shift the incoming bits into the mantissa such that these would form a range between 0 and 1. Listing 5.16 with bit manipulation is the best result that I could achieve. With an exponent of -1 represented as this, 126 in base 10, the source byte achieves a range of 0.5 to 0.998. That can be normalized to 0.0 to 0.996 with subtraction and multiplication. But is there a better way to do this? As a complete program, you can incorporate mock_rand from listing 5.16 into a test program fairly easily. Listing 5.17 in this file. generates an F32 value that lies between 0 and 1 from an arbitrary input byte without division. Here is its output. Section 5.7. Implementing a CPU to establish that functions are also data. One of the fairly mundane yet utterly intriguing details about computing is that instructions are also just numbers. Operations and data that is being operated on share the same encoding. This means that, as a general computing device, your computer can emulate other computers' instruction sets by emulating those in software. While we cannot pull apart a CPU to see how it works, we can construct one with code. After working through this section, you will learn how a computer operates at a fundamental level. This section shows how functions operate and what the term pointer means. We won't have an assembly language. We'll actually be programming directly in hex. This section also introduces you to another term you may have heard of in passing, the stack. We'll implement a subset of a system called Chip 8, which was available to consumers in the 1970s. Chip 8 was supported by a number of manufacturers, but it was fairly primitive even by the standards of the time. It was created to write games rather than for commercial or scientific applications. One device that used the Chip 8 CPU was the Cosmac VIP. It had a single-color display with a resolution of 64 by 32, or 0.0002 megapixels, 2 kilobytes of RAM, 1.76 megahertz CPU, and sold for $275 US. Oh, and you needed to assemble the computer yourself. It also contained games programmed by the world's first female game developer, Joyce Weisbecker. Section 5.7.1. CPU RIA/1, the adder. We'll build our understanding by starting with a minimal core. First, let's construct an emulator that only supports a single instruction, addition. To understand what's happening within listing 5.22 later in this section, there are three main things to learn. Becoming familiar with new terminology. How to interpret opcodes. Understanding the main loop. Terms related to CPU emulation. Dealing with CPUs and emulation involves learning some terms. Take a moment to look at and understand the following. An operation, often shortened to op, refers to procedures that are supported natively by the system. You might also encounter equivalent phrases such as implemented in hardware or intrinsic operation as you explore further. Registers are containers for data that the CPU accesses directly. For most operations, operands must be moved to registers for an operation to function. For the Chip 8, each register is a U8 value. An opcode is a number that maps to an operation. On the Chip 8 platform, opcodes include both the operation and the operand's register. Defining the CPU. The first operation that we want to support is addition. The operation takes two registers, X and Y, as operands and adds the value stored in Y to X. To implement this, we'll use the minimal amount of code possible, as the following listing shows. Our initial CPU contains only two registers and the space for a single opcode. So far, the CPU is inert. To perform addition, we'll need to take the following steps, but there's no ability to store data in memory as yet. 1. Initialize the CPU. 2. Load U8 values into registers. 3. Load the addition opcode into current_operation. 4. Perform the operation. Loading values into registers. The process for booting up the CPU consists of writing to the fields of the CPU struct. The following listing, an extract from listing 5.22, shows the CPU initialization process. Line 38 from listing 5.19 is difficult to interpret without context. The constant 0 times 8014 is the opcode that the CPU will interpret. To decode it, split it into 4 parts. 8 signifies that the operation involves 2 registers. 0 maps to CPU.registers 0. 1 maps to CPU.registers 1. 4 indicates addition. Understanding the emulator's main loop. Now that we've loaded the data, the CPU is almost able to do some work. The run method performs the bulk of our emulator's work. Using the following steps, it emulates CPU cycles. 1 reads the opcode, eventually from memory. 2 decodes instruction. 3 matches decoded instruction to known opcodes. 4 dispatches execution of the operation to a specific function. The following listing, an extract from listing 5.22, shows the first functionality being added to the emulator. How to interpret chip 8 opcodes. It is important for our CPU to be able to interpret its opcode, 0 times 8014. This section provides a thorough explanation of the process used in the chip 8 and its naming conventions. Chip 8 opcodes are U16 values made up of 4 nibbles. A nibble is half a byte. That is, a nibble is a 4-bit value. Because there isn't a 4-bit type in Rust, splitting the U16 value into those parts is fiddly. To make matters more complicated, chip 8 nibbles are often recombined to form either 8-bit or 12-bit values depending on the context. To simplify talking about the parts of each opcode, let's introduce some standard terminology. Each opcode is made up of 2 bytes, the high byte and the low byte. And each byte is made up of 2 nibbles, the high nibble and the low nibble, respectively. Figure 5.2 illustrates each term. Documentation manuals for the chip 8 introduce several variables, including KK, NNN, X, and Y. Table 5.2 explains their role, location, and width. There are 3 main forms of opcodes, as illustrated in Figure 5.3. The decoding process involves matching on the high nibble of the first byte and then applying one of 3 strategies. To extract nibbles from bytes, we'll need to use the right shift, or greater than, and logical and, ampersand, bitwise operations. These operations were introduced in Section 5.4. Especially in sections 5.4.1 through 5.4.3. The following listing demonstrates applying these bitwise operations to the current problem. Now, we're able to decode the instructions. The next step is actually executing these. Section 5.7.2. Full code listing for CPU RIA/1, the adder. The following listing is the full code for our proto-emulator, the adder. You'll find its source in this file. The adder doesn't do much. When executed, it prints the following line. Section 5.7.3. CPU RIA/2, the multiplier. CPU RIA/1 can execute a single instruction, addition. CPU RIA/2, the multiplier, can execute several instructions in sequence. The multiplier includes RAM, a working main loop, and a variable that indicates which instruction to execute next that we'll call position_in_memory. Listing 5.26 makes the following substantive changes to listing 5.22. Adds 4 kilobytes of memory, line 8. Includes a fully fledged main loop and stopping condition, lines 14 through 31. At each step in the loop, memory at position_in_memory is accessed and decoded into an opcode. Position_in_memory is then incremented to the next memory address, and the opcode is executed. The CPU continues to run forever until the stopping condition, an opcode of 0 times 0000, is encountered. Removes the current_instruction field of the CPU struct, which is replaced by a section of the main loop that decodes bytes from memory, lines 15 through 17. Writes the opcodes into memory, lines 51 through 53. Expanding the CPU to support memory. We need to implement some modifications to make our CPU more useful. To start, the computer needs memory. Listing 5.23, an extract from Listing 5.26, provides CPU RIA/2's definition. CPU RIA/2 contains general-purpose registers for calculations, registers, and one special-purpose register, position_in_memory. For convenience, we'll also include the system's memory within the CPU struct itself as the memory field. Some features of the CPU are quite novel. Having 16 registers means that a single hexadecimal number, 0 to F, can address those. That allows all opcodes to be compactly represented as U16 values. The chip 8 only has 4,096 bytes of RAM, 0 times 1,000 in hexadecimal. This allows chip 8's equivalent of a U-size type to be 12 bits wide. 2 to the 12th equals 4,996. Those 12 bits become the NNN variable discussed earlier. Rust in action deviates from standard practice in two ways. What we call the position in memory is normally referred to as the program counter. As a beginner, it can be difficult to remember what the program counter's role is, so instead, this book uses a name that reflects its usage. Within the chip 8 specification, the first 512 bytes, 0 times 100, are reserved for the system, while other bytes are available for programs. This implementation relaxes that restriction. Reading opcodes from memory. With the addition of memory within the CPU, the read_opcode method requires updating. The following listing, an extract from Listing 5.26, does that for us. It reads an opcode from memory by combining two U8 values into a single U16 value. Handling integer overflow. Within the chip 8, we use the last register as a carry flag. When set, this flag indicates that an operation has overflowed the U8 register size. The following listing, an extract from the Listing 5.26, shows how to handle this overflow. Full code listing for CPU RIA/2, the multiplier. The following listing shows the complete code for our second working emulator, the multiplier. You'll find the source for this listing in this file. When executed, CPU RIA/2 prints its impressive mathematical calculations. Section 5.7.4. CPU RIA/3, the caller. We have nearly built all of the emulator machinery. This section adds the ability for you to call functions. There is no programming language support, however, so any programs still need to be written in binary. In addition to implementing functions, this section validates an assertion made at the start. Functions are also data. Expanding the CPU to include support for a stack. To build functions, we need to implement some additional opcodes. These are as follows. The call opcode, 0 times 2 NNN, where NNN is a memory address, sets position_in_memory to NNN, the address of the function. The return opcode, 0 times 00EE, sets position_in_memory to the memory address of the previous call opcode. To enable these opcodes to work together, the CPU needs to have some specialized memory available for storing addresses. This is known as the stack. Each call opcode adds an address to the stack by incrementing the stack pointer and writing NNN to that position in the stack. Each return opcode removes the top address by decrementing the stack pointer. The following listing, an extract from listing 5.29, provides the details to emulate the CPU. Defining a function and loading it into memory. Within computer science, a function is just a sequence of bytes that can be executed by a CPU. CPUs start at the first opcode, then make their way to the end. The next few code snippets demonstrate how it's possible to move from a sequence of bytes, then convert that into executable code within CPU RIA/3. Footnote 4. The sequence of bytes must also be tagged as executable. The tagging process is explained in section 6.1.4. 1. Define the function. Our function performs two addition operations and then returns. Modest yet informative. It is 3 opcodes long. The function's internals look like this in a notation that resembles assembly language. 2. Convert opcodes into Rust data types. Translating these 3 opcodes into Rust's array syntax involves wrapping them in square brackets and using a comma for each number. The function has now become a U16:3 wrapped in square brackets. We want to be able to deal with 1 byte in the next step, so we'll decompose the U16:3 wrapped in square brackets array further into a U8:6 wrapped in square brackets array. 3. Load the function into RAM. Assuming that we wish to load that function into memory address 0 × 100, here are 2 options. First, if we have our function available as a slice, we can copy it across to memory with the copy_from_slice method. An alternative approach that achieves the same effect within memory without requiring a temporary array is to overwrite bytes directly. The approach taken in the last snippet is exactly what is used within the main function of lines 96 through 98 of listing 5.29. Now that we know how to load a function into memory, it's time to learn how to instruct a CPU to actually call it. Implementing the call and return opcodes. Calling a function is a 3-step process. 1. Store the current memory location on the stack. 2. Increment the stack pointer. 3. Set the current memory location to the intended memory address. Returning from a function involves reversing the calling process. 1. Decrement the stack pointer. 2. Retrieve the calling memory address from the stack. 3. Set the current memory location to the intended memory address. The following listing, an extract from listing 5.29, focuses on the call and ret methods. Full code listing for CPU RIA/3, the caller. Now that we have all the pieces ready, let's assemble those into a working program. Listing 5.29 is able to compute a hard-coded mathematical expression. Here is its output. This calculation is made without the source code that you may be used to. You will need to make do with interpreting hexadecimal numbers. To help, Figure 5.4 illustrates what happens within the CPU during CPU.run. The arrows reflect the state of the CPU.position_in_memory variable as it makes its way through the program. Listing 5.29